right. Well, welcome back. Today's lesson is about kind of starting to take that next step about using the molar quantity or the molar mass quantity, and now kind of being able to drill in a little bit further, not just doing something simple like telling me how many molecules are present or how many atoms are present, but really being able to use molar quantities to start to analyze the composition of certain compounds. And so the next series of videos will kind of do a couple of these, but this is one of the really reasons why the mole concept is actually really useful for us. Imagine that you've just found a plant or something that's got the cure for cancer, the cure for COVID in it, and you want to try to isolate, well, which compound is it? There's all these different compounds inside a plant or an animal or a bacterium or whatever. Being able to isolate that compound and then go further, not just know that you have the compound, but then to actually figure out what its chemical formula is actually a lot more challenging than you'd think it would be. You think you just have to plug it in a machine, it would tell you, but it really doesn't. I mean, they've gotten better certainly in the last few years. But this idea of trying to be able to determine chemical composition or chemical formulas based on lab data or lab information is sort of important. So we're going to start off with the easier part, which is, I guess I'll switch my screen here. We're going to start off with the easier part, which will be to start off with percent composition. And that's the one that's in this particular video. And then we'll get into the harder one in the next series, which is empirical and molecular formulas. So make sure that you're comfortable. You've got your periodic table nearby. You've got your handy dandy calculator nearby so that you're ready to kind of calculate along with me, shall we? But again, this particular one is the easier one about doing percent composition, because that's usually the first kind of thing that we do, right? We'll isolate some new compound and we'll go, okay, well, first of all, what elements are present? And second of all, how much of each element is present? And percent composition is sort of the simplest way that we would address that. So percent composition, just so you know, if I can get this to move forward, percent composition, just so you know, is also known as mass percent. Those two phrases are equal. Mass percent, percent composition, they mean the same thing. So don't let that one trip you up. I'm not trying to tease you or something like that. If you've got that particular, like, wait, what is she asking about now? Those are actually synonyms at this point. So let me get my pen going here. So let me give you an example of how percent composition can give us some insight. So we're going to take a look at the percent composition or the mass percent of water versus hydrogen peroxide. So here's water, right? Here's hydrogen peroxide. And this is one of those original ways that they realized that there were some of these compounds that existed that had more than one different formula, even though the same elements were present. Remember, that's called the law of multiple proportions. So we've got H2O versus H2O2. And how can we tell something different about it? Well, mass percent, we are literally going to be using masses from this. So this is periodic table information. And we use the formula in this. So don't make this too hard. Percent composition is not a super challenging math thing to do. So what we're going to look at here is, okay, water contains 2 atoms of hydrogen and 1 atom of oxygen. So we're going to do this by mass, though, not by number of atoms. We're not going to say that, well, there's 3 atoms present and 2 of the 3 atoms are hydrogen. This is mass percent that we are referring to, because that's what we can actually identify in a lab situation if we don't know what the formula is. So we would do something like this. I would say, all right, for H2O, there are 2 atoms of hydrogen, and hydrogen weighs 1.01 grams per mole. There is 1 atom of oxygen, which weighs 16.00 grams per mole. And then we try to figure out what this total mass is. So here's how I like to do these when I'm doing percent composition. I will kind of do one element at a time. So I would do the 1.01 times 2, 2.02. I would do the 16 times 1, 16.00. And then I would figure out what my combined mass is, which here is 18.02. Then you go back and do your percents. Now remember, percent is part divided by whole. Always, whenever you're doing it, percents is always part over whole. And then we do the times 100 because it's a percent. That's actually what the word percent means. It means per 100%. So you always have that in there. A lot of times I don't say the per 100 because I figure as honor students, you should probably know that there's 100 in there, but just in case. So we've got our 2 parts. One of our parts is the hydrogen part, and then we've got one of our parts is the oxygen part, and then we have our whole, which is the combined mass of the 2 of them. So if I want to figure out the mass percent of water, I would look at, well, what's the mass percent of hydrogen in water? And I would literally do 2.02 divided by 18.02. So if I want to know the percent of hydrogen, again, that's the part that we are doing, it's 2.02 divided by 18.02 times 100. When I do this on my calculator, I get a mass percent of 11 point something or other. Now we'll take a look at this. We've got 2 decimal places here. Maintain those 2 decimal places. That's kind of a sig figs rule, sort of exception, I guess if you want to call it that, but it is definitely one of our rules because the way we're doing the percents, it's similar to that. Don't worry so much about like this has 3 sig figs and 4 sig figs. Keep your decimal places when we're doing percents. Trust me. So this would tell us that this is 11.21% hydrogen in this particular step because oxygen is quite a bit heavier. Then I'm going to do 16.00 divided by 18.02. Again, the oxygen part divided by the whole. And this gives me a percent here of 88.79%. And yes, these should add up to 100 if you've done it right. So I would not do the 100 minus 11.21 to figure out the other one, just in case. It'll help you actually catch your errors. But at the end, to go back and do that quick check, do these add up to 100? And yes, they do. So water is 11.21% hydrogen and 88.79% oxygen. That's kind of how we would do that. So let's compare that to what's going on in H2O2 because it's similar, but a little bit different. So if we do this one, H2O2, and again, this would be a good time for you to pause and apply your knowledge to it because it should be done pretty similarly to it. So H2O2, got to do part divided by whole. So hydrogen versus oxygen. Hydrogen is 1.01 grams per mole, and there are 2 hydrogens present in this particular compound. That's 2.02. Oxygen is 16 grams per mole, and there are 2 oxygens in each of these molecules. Or if we had a mole of molecules, we would have 2 times that many. So that is 32.00. Our combined mass now is 34.02. So again, to do our percent composition, we would do the mass percent of hydrogen, and then we would also do the mass percent of oxygen. So the mass percent of hydrogen is the part that's hydrogen divided by the whole mass. So 2.02, that's hydrogen's part, divided by 34.02, that's H2O2's whole mass. And that gives us a value of, let's see, 5.94%. Quite a bit less, right? Which is weird because it's the same number of atoms, but there's another oxygen there, so it's less percentage by mass. And then our oxygen would be 32 divided by 34.02. It should be, right around 95%. And we get, 32 divided by 34.02. Nice job, Bedwell. We get 94.06% oxygen. So again, by doing some simple analysis, if we had a machine that could take a sample of a clear liquid, dump it in there, and tell me what the percent composition was, what's percent hydrogen versus percent oxygen overall, and there are machines that do this, then I could easily tell the difference between water, which is 11% hydrogen, 88%, 89% oxygen, hydrogen peroxide, which is only 6% hydrogen and 94% oxygen. So mass percent can really tell us something about the composition. Now we have to do a little bit more work to get formulas. We'll get that in the next one. By the way, the name of the thing that does this, spectrometer. The name of the equipment that's capable of doing this for us is something called a mass spectrometer. That's the thing that can actually, you can put a compound in and it can tell you what percent of the different masses are present. So just so you know, FYI, if you're interested. Okay, so let's apply this. Let's take a look at the percent composition of glucose and the percent composition of sucrose. I tried to pick two compounds here that had similar elements in it. They both have carbon, hydrogen, oxygen, because it makes our lives a little bit easier. So if we've got carbon, carbon is, here's how I would normally set these up. Carbon's mass, its molar mass, 12.01. And then there are 6 atoms of carbon in each one of these molecules. Hydrogen would be 1.01 times 12. By the way, 12.01, 1.01, again, those are coming from your periodic table. Those are molar masses. Times 12, because there's 12 atoms in there, right? And then oxygen is going to be 16.00 times 6 atoms in there. So I'm taking this molecule apart. If I had a mole of these things, this would give me my kind of ratios to it. So now I'm going to figure out what each of those is. Let's see, 12.01 times 6 is 7206, 72.06. 1.01 times 12 is 1212, 12.12. And then 16 times 6, if I could do it right, 16 times 6, my 6 button doesn't work on my calculator very well, 96.00. So my total mass, now I have to add all these together, right? What's the combined? Each one of these is the part. This is the part that's carbon, the part that's hydrogen, the part that's oxygen. The combined mass is 96 plus 12.12 plus 72.06. Again, the combined mass is 0.06. And I get a combined mass of 180.18. There we go. So now to do our percents, we literally just do this. Part divided by whole. 180.18, 180.18, 180.18. Again, this is the part, and this is the whole. And again, each one of these you would do times 100 because we're trying to turn it into percent form, not decimal form. So 72.06 divided by 180.18. Again, this is kind of the boring part. This is 39.99. 39.99 percent carbon. And that's how you do units and labels. I guess percent is kind of the unit here. 1212 divided by 180.18 is 6.73% hydrogen. Again, with our percents, we're going to keep those 2 decimal places. And then 96 divided by 180.18 is 53.28% oxygen. So there you go. Basically 40% carbon, 6 to 7% hydrogen, and was that 53-ish percent oxygen. And that's by mass, so that's our percent composition. So this is a really good chance for you to hit pause and see if you can practice this with sucrose. See if you can figure this one out. Again, it's a good practice spot for you to take care of this. So I'm going to start kind of writing mine on there. 12.01 times 11. I've got hydrogen is 1.01 times 22. Man, sucrose is big. Oxygen is going to be 16.00 times 11. Yeah, this is going to be a big, heavy molecule. A lot to it. 12.01 times 11. Oh, that's a big number. 132. 132.11, 1.01 times 22. You can kind of see how I'm setting it up on the paper because for me, this actually reduces the amount of work that I have to do and like numbers I have to go back and find and refine. For me, I have found this to be the fastest way, but you can set it up on the paper a bunch of different ways. It's not like setting it up in like rows and all this stuff like I'm showing you on the screen is any particular formal method. Like I said, for me, this has always been the part that's just been like the least amount of paper, least amount of space, kind of set it up in a way that works. So 176, not 176.1, sorry, it's 176. My apologies. All right, I'm going to get my total mass, 176 plus 22.22 plus 132.11. Okay, so now what I've done is I've taken my compound apart. I found each of the parts, 330.33, and now I have found the whole. So there's the part that is carbon. Here's the part that is hydrogen, 22.22. And here's the part of the mass that would be oxygen, 176. Here's our total mass, 330.33. So I'm going to do my kind of repeat division here, 330.33, 330.33, and then I'll figure out what my percentages are. So 132.11 divided by 330.33. Yeah, it's kind of repetitious. Okay. 39.993% carbon. 22.22 divided by 330.33 is 0.6.73% hydrogen. Okay. And then my last one, 176 divided by 330.33 is 53.288% oxygen. So the reason why I do these two is so that you can see why percent composition is easy, right? It's a nice, easy bit of math to do. Most people can get their brains wrapped around this and figure this one out really quick. So why do we have to do any more than that? And this is why. There's a problem in chemistry where percent composition gives us an insight, but it doesn't really tell us something different. So here we have two very different chemical compounds, not very different, I guess. They're both sugars, but we have glucose and sucrose, very different sizes. Like sucrose is twice as big, almost twice as big as glucose is. By the way, did you get what the joke is right here? Yeah. Okay. It's a good joke, man. Come on. What kind of car is it? What kind of compound is it? It's a joke. Anyway, so if you take a look at these two side by side, when you analyze the percent composition of glucose and you analyze the percent composition of sucrose, they're exactly the same. In fact, you can take any kind of sugar, fructose, maltose, lactose, any of them. And when you analyze them according to percent composition, they look the same. There's a piece that's missing from percent composition. And that's the empirical formulas piece that I'll do in the next problem. But this is why we have to do something other than percent composition. It's a really good first start, but it doesn't give us everything that we need to really know what the formula is of a particular compound, or really to be able to identify, sometimes even to be able to tell the difference between two different compounds. And in our next lesson, that's what we'll do next, is that we'll talk about how do we take it that next step, right? How do we actually go and get formulas from information like percent composition, okay? So there you go. Relatively straightforward math calculations in terms of doing percent composition. Now you've kind of learned what it is, why it works, and then also why it's a little bit on the weaker side, why it isn't quite enough for us. There you go. Hope you liked it. I'll see you in the next video.